So we have 3 S's, we have 1 U, and then we have 2 C's and an E, right? And it says that the first letter must be a U, right? So we just cross out the U. Okay, so let's get rid of that U. And then at this point, guys, we just set up the combinations just like we normally would, okay? So I think the way we might set this up, and correct me if I'm wrong, we have 6 letters. Of those, we want 3 for the S's. And then we have 3 letters. We want 2 for the C's. And then we have 1 letter, of which we're going to get 1, or we could do 1 factorial if we really wanted to, although that doesn't really help us. So, does that setup look okay to everybody, guys? Any questions about that? Okay. Now our job is just to do the computations and then be done with this problem. Okay, so 3, 2 is 3, 1, 1 is 1, and then 6, 3, anyone got that one?
20.
20, okay. So we get 60 out of this. Not necessarily all that exciting, but not too difficult. Okay. Better than a mathematical proof by function, right guys? Okay. All right, questions I can answer, guys, about being able to do these counting methods? Okay, hopefully not too difficult. John, go ahead, sir.
For C, do you just ignore the M that's at the beginning?
Correct, right. The reason we do that is because we just took it out and it's already been placed into its own spot. Okay, so that M has no more bearing on the problem whatsoever.
Yeah, so it's as if you like took it out and it would be the same.
Right, and then what that means is instead of working with 11 letters, now you're working with 10 letters.
Yeah.
Okay, so it just basically creates a new word, if you would, or a new number of letters you're selecting from. Okay. Other questions, guys? Okay, so we're all done with the counting method stuff. We're still going to work with combinations and permutations, but this time we're actually going to be proving some stuff with it. Okay, so, and I know how much you guys like proofs. It's the only thing that makes this class fun, right? Yeah, sure. So I'll wait till everyone gets copies of these. What's up? Oh, I didn't give you guys enough? I was too.
Oh, thank you.
You're welcome, man. Okay, sorry about that, guys. Okay, anybody else need a copy, or everybody got one? Okay. So essentially, we've been working with the idea of applying the definitions of permutation and combinations. Now we're going to prove some of these. Okay. So essentially, what we're going to do is, if I give you a property, you're going to prove it. Okay. And we just have to remember the definition of permutation, the definition of combination. So let's write that out just to make sure we remember. Okay. So we have a permutation. Okay. Permutation n comma r is equal to n factorial divided by n minus r factorial. Okay, so that's our definition. And essentially what we're going to be doing is we're going to be substituting the values back into there and then just proving. Okay, so most of these guys are just algebra problems. Okay, now we are going to have some factorials with common denominators, so that might get a little bit dicey for some of you guys. So what we're probably going to do this afternoon is we're probably going to prove the first 2 of these. Sorry about that, I didn't mean to roll away. We'll probably prove the first 2 of these, and then next time we'll prove the rest of them. Okay. So, I give you guys a problem to where for all integers n, for where n is bigger than or equal to 2, regardless of what the number is, the permutation n plus 1 comma 3 is equal to n cubed minus n. Okay. So, let's go ahead and prove that. We start with n plus 1 representing the n, and then 3 representing the r. So wherever I see an n, I'm going to plug in n plus 1. Wherever I see an r, I'm going to plug in 3. So basically we start by doing substitution. Okay? So, permutation n plus 1 comma 3 is going to be equal to n plus 1 fact. Okay? So all I'm doing is wherever I see an n, I'm plugging in n plus 1, divided by n plus 1 minus 3 fact. So let me make sure that's okay with everybody. Okay? All I did there was I just substituted n plus 1 for n, 3 for r. Is that okay with everybody, guys? Just using the definition of permutation. Okay? If I was to ask you guys to prove this, I don't think there's anybody in here that wouldn't just subtract 1 and 3, right? You would just combine that in the parentheses. So this would wind up being n plus 1 fact divided by n minus 2 quantity fact, right? Okay. That's easy. I mean, nobody in here can get that wrong. Now, we need to prove that it's equal to n cubed minus n. Okay, so does anyone maybe have a suggestion as to perhaps how to simplify this? Or
Do n plus 1 multiplied by n, then n minus 1, then n minus 2, then n minus 2, and you, what you say, cancel them out.
Yeah, this is stuff that we did in the last examination where you simplify factorial expressions. Basically, extend the definition of the factorial. So let's do that, okay? So n plus 1 factorial is equal to n plus 1 times n minus 1 times n minus 2 all the way down to 1, right guys? That's the definition of n plus 1 factorial. Okay. And that's still divided by n minus 2 fact. But n minus 2 fact, if I was to expand that, would be n minus 2, n minus 3, all the way down to 3, 2, 1. Okay, so all we did there, guys, was we just utilized the definition of factorial. And remember, factorial means you just multiply in descending order. Okay, is that okay, guys? Any questions about what we did there? Okay. Or would you say to do it at this point?
N minus 2 and n minus 3 can cancel them out.
Yeah. Any factor n minus 2 or lower is going to cancel out. And I think now everybody can see that this is going to really nicely work into n cubed minus n. I'll still show you guys how it works out to be that, okay? But I'm betting most of you guys are like, oh, okay, now I can see that there's going to be a cubic term in there by the multiplication, okay? So let's go ahead and finish this, okay? I'm going to take the n and I'm going to distribute it. Remember, guys, when you have a singular monomial and you want to distribute it, you don't...
Actually, that's a perfect square. N squared minus 1.
We could do that and get the n squared minus 1 out of that, or we could just distribute. It doesn't really matter, right? But yeah, you're right. Okay. So this would become n squared plus n, and then n minus 1. Now we just FOIL it out, okay? And then eventually we can combine some like terms. So after FOIL, we get n cubed, and then we get minus n squared, plus n squared minus n, okay, just by doing the first outer inner last on that. And then I think it's pretty obvious that the inner terms of n squared are going to cancel each other out. So I think we wind up with n cubed minus n. So guys, essentially all I'm asking you guys to do is to use the definition of the factorial to be able to simplify and to work with what we have for our for these permutations. I mean, does that make sense to everybody, guys?
Then what is the reason of giving n is greater than 2?
Well, because if it's nr, think of, if I asked you to pick 5 elements from 3,
Okay.
you can't do that. So this first number has to be at least as big as the second number. And the only way to guarantee that is to make it
got
n2
into
or
the
better.
domain. I got it.
Okay? So otherwise you can't, it's just outside the domain of a permutation. Does that make sense, Art?
Got
It really has no bearing on the algebra of it. It's just making sure that the domain is specified for the problem. It's like when you're doing an integral and you get like the ln, if you forget the absolute values, technically it's wrong, but your teacher might not mark you wrong sort of thing, because it's domain thing. All right, other questions, guys? Okay, so that one wasn't too bad, okay? Now, unfortunately, the second one's a lot uglier, okay? So let's go ahead and tackle that one. So this one says that, again, for all n bigger than or equal to 2, permutation n plus 1 comma 2 minus permutation n comma 2 is equal to 2 permutations n1. Okay, so what we want to do with this, guys, is work with the more complex side. You don't want to work with the easier side, try to make it look like the harder. There's just no way. Well, there is. You'd have to do partial fraction decomposition, and you don't want to deal with that if you don't have to. Okay, so let's go ahead and just try to simplify the left-hand side. Okay, so I have permutation. I'm just rewriting this. You guys don't have to do this again. I'm just rewriting it for my own benefit. Minus Pn comma 2. We're going to use the definition of permutation. So this is n plus 1 fact divided by n plus 1 minus 2 fact minus n fact divided by n minus 2 fact. Okay, and that's for this fraction right here. So, everyone get a look at that and make sure everything's okay. So, any questions about how we set that up, guys, before we go on? Okay, everybody feels good about substituting and being able to work with the substitution for a permutation. Okay, I can't imagine that anybody wouldn't know what to do next with this, because in the first fraction's denominator, there's an n plus 1 minus 2, which just happens to be the exact same expression that we ended up with last time, I think, except instead of n minus 2, it's n minus 1. So now we're going to get n plus 1 fact divided by n minus 1 fact minus n fact divided by n minus 2 fact. Okay. Now, what I see a lot of students try to do is I see a lot of students try to cancel out terms, because they're like, oh, okay, I can expand n plus 1 and I can expand n minus 1 factorial. But what happens if you expand and cancel? What are you never going to get to on the right-hand side? You'll never get to 2 permutations of anything. You'll get to a polynomial, but you won't get to a permutation, okay? So, because it's being equal to a permutation and not a polynomial, we can't use the canceling stuff, okay? So does that make sense, guys, as to why we can't cancel, okay? All right. So the question is, what do we do? Well, we need to somehow make this into a singular fraction, I think, okay? If we can get a single, go ahead, we need a common denominator, right? Guys, if we get a common denominator, then at least we might have a punching chance of getting the 2 permutation n1, okay? So the question is, though, what is the common denominator between n minus 1 fact and n minus 2 fact? So,
multiply both of them.
no. You don't want to do that. You're going to be, that would make this problem so ridiculously difficult, nobody would want to do it. Okay? It's actually n minus 1 factorial. Okay, let me illustrate why. Okay, I'm going to do this off to the side. You guys don't have to write this. Okay. N minus 1 factorial is what? N minus 1, n minus 2, n minus 3, 3, 2, 1, right guys? N minus 2 factorial, which is the other denominator, is going to be n minus 2, n minus 3, all the way down to 3, 2, 1. Okay? Guys, don't both of those expressions share every single factor
Except n minus 1.
except for n minus 1, right guys? So if I was to just simply do, what could I do to make n minus 2 fact look like n minus 1 fact? Yeah, multiply both sides of that equation by n minus 1, right? If I multiply right here by n minus 1 on both sides, this would make it look exactly like n minus 1, okay? Art, do you understand that if you multiply those together, you would get n minus 2 squared, n minus 3 squared, n minus 4 squared. And then you'd have to multiply all the numerators by all those missing factors, okay? there's just no way we could do that, okay? It would just be too ugly, okay? So, and I wasn't trying to pick on you. It's not a bad idea. If you're ever confused like with fractions, you usually just multiply them together and brute force it. This one, though, it would be so brutal that you couldn't overcome it. Okay, so now what we're going to do is by least common denominator, we are going to rewrite these. Okay, so we're going to have an n minus 1 fact, and we're going to have an n minus 1 fact. Okay, so all we're doing here is we're just getting a least common denominator. Okay, in fact, let's make a note of that. That the LCD, I'll get out of your guys' way, I know, is n minus 1 factorial. And if you don't believe me, look in the upper right-hand corner and you can see that all the factors are common except for n minus 1. It's the only one that we don't have. All right. Now, just like any fraction, you have to play that game of whatever's missing on top, you have to multiply to maintain equivalence of the fraction. Okay? To go from n minus 1 fact to n minus 1 fact in the first fraction. What do we multiply the numerator by, if anything?
Okay.
Nothing, right? It stayed the same. So the first numerator is going to stay n plus 1 fact. However, the second fraction, what do we have to multiply n minus 2 fact by to get to n minus 1
n
fact?
minus 1.
N minus 1, right? Guys, can't we see right here that we are missing n minus 1? So, if that's what we're missing, that's what we have to multiply the numerator by to maintain equivalence. Okay, does that make sense to everybody, guys? It's just like any other fraction. Whatever you're missing to go from one fraction to the next, that's what you multiply by. So we're going to have n fact, n minus 1. All right. So, everybody good, guys? Any questions thus far? Okay. That's a technique, by the way, that you guys are going to have to use quite often. Okay? When we start doing stuff with the binomial theorem, we're going to see this again. Okay? So, we'll see this a couple more times, but it's definitely something that you guys are going to have to utilize as we